Hello everyone, myself Varshita S. from Sri Venkateshwara College of Engineering. Today we will going to discuss about computer graphics. In that we will going to discuss about three topics. First one is 2D weaving pipeline and 3D weaving pipeline and the RGB color models. First we will going to discuss about 2D weaving pipeline. The two-dimensional weaving in computer graphics is a technique to map the world coordinate systems. That means actual coordinates of the objects in the real world to device coordinates, that is actual coordinates of the objects on the output screens like a monitor. In computer graphics, to perform a weaving transformations, we need a tool called OpenGL. The basic OpenGL library do not support the functions for 2D weaving transformation as they are made especially for 3D weaving transformation, but we can apply 3D weaving routines to 2D weaving scenes. We can use the two-dimensional routines along with the OpenGL viewport functions. That two-dimensional routines that can be used are GLU library functions and GLUT library function. Next, the GLU clipping window functions. This function is used to define a two-dimensional clipping window, and the syntax for this is GLU ortho to 2D XW minimum, XW maximum, YW minimum, and YW maximum. And second one is the GLUT display window. This function is used to initialize the GLUT. The GLUT means Graphic Library Utility Toolkit. Next, this is the diagram for the 2D weaving pipeline. First, the object coordinates will pass here, the construction of the objects and the scenes, and the word coordinate will be produced here. This is the definition of mapping region orientations, and the weaving coordinates will be passed here. Projection onto unity image region, and the normal device coordinates will passed here. The transformation of specific device and the device coordinates will produced here. The coordinates in which individual objects model are created are called model or object model coordinates. When several objects are assembled into a scene, they are described by word coordinates. And after transformation into the coordinate system of the camera, that is weaver, they become a weaving coordinates. Their projection onto a common plane, that is window, yields to device independent normalized coordinates. Finally, after mapping those normalized coordinates to a specific device, we get to the device coordinates. Next, we will move on to the 3D weaving pipeline. This is the basic diagram for 3D weaving pipeline. First of all, we need to choose a weaving position corresponding to where we would place a camera. We choose the weaving position according to whether we want to display a front, back, or side, or top, or bottom of the weaving scenes. We could also pick a positions in the middle of the group of the objects, or even inside a single object, such as a building or a molecules. Then we must decide on the camera orientations. And this 3D weaving pipeline consists of 5 transformation. First one is the modeling transformation and weaving transformation, and this weaving transformations is connected to the projection transformation, and it will connect to the normalized transformation and the clipping, and the normalized clipping will move on to the viewport transformation, and the device coordinates will produce. Finally, when we snap the shutter, the scene is cropped to the size of a selected clipping window, which corresponding to the aperture or lens type of a camera, and light from the visible surface is projected onto the camera film. Some of the weaving operations for a 3D dimensional scenes are the same as or similar to those used in the 2D two-dimensional weaving pipeline. Two-dimensional viewport is used to position a projected view of the three-dimensional scenes on the output devices. And a two-dimensional clipping window is used to select a view that is to be mapped to the viewport. The clipping windows, viewports, and display windows are usually specified as a rectangle with their heads parallel to the coordinate axis. And the viewing positions, viewplane, clipping window, and clipping planes are all specified within the viewing port reference the frame. Next, we will move on to the RGB color model. According to the tristimulus theory of visions, our eyes perceives color through the stimulation of three visual pigments in the cone of the retina. One of the pigments is most sensitive to light within a wavelength of about 360 nanometer, that is red. Another has its peak sensitivity at about 530 nanometer, that is green color. And the third pigment is most receptive to light with a wavelength of about 450 nanometer, that is blue. These three primaries, red, green, and blue, which is referred as the RGB color model. You can represent this model using the unit cube defined R, G, and B axis as shown in this figure. Let us take in x-axis as red and y-axis as green and z-axis as blue. And combination of red and green will produce the yellow color, and the combination of green and blue produces the cyan color, and the combination of blue and red will produce the magenta color. And at the center, the black color will placed, and a combination of these two will produce us the white color, and this dotted line is represent as a grayscale. In the origin represents the black, and the diagonally opposite vertex with the vertex 111 is white. The RGB color scheme is an additive model. Each color point within the unit cube can be represented as a weighted vector sum of the primary colors. Using a unit vectors R, G, and B, C lambda equals to R, G, B equals to RR plus GG plus BB, where the parameters R, G, and B are assigned the values in the range from 0 to 1.0. Thank you.